Okay, in this video, I would like to talk about the process of evaluating limits. And in this video, you're going to hear me referring to a plan A and a plan B. Now, plan A is very straightforward. There's a value that x is approaching, plug in that value, and we're done. Plan B is what we fall back on, basically, if we can't plug in the limit value. And we'll get into some specific examples. There's about 10 of them in this video about when you can and cannot use direct substitution. So before we get started, I want to take like a graphical approach to when you can and cannot plug in the limit value. So let's say here we're in, we have some function, so let's call it, let's say it's there, it's f of x, and we want the limit as x approaches c of the function f of x. Well, if this is c, well then, here's the point on the graph, and here is f of c. So as the x values approach c from above and below, the y values are getting closer to f of c. And so f of c is defined, and we have a point on the graph, so the function is continuous. Now we'll talk about we'll formally define this idea of continuous or continuity in a later video, but for right now, let's just say there's no holes, there's no jumps, there's no asymptotes here when x is equal to c. So in this case, when the function is continuous, or when f of c is defined and the point c comma f of c is on some continuous portion of the graph, we can evaluate the limit by direct substitution. Now, when this approach fails is when we have something like, well, if this is c, and maybe our graph looks like this. There's a hole at c. Or maybe our graph looks like this. There's a jump at c. So these are two types of discontinuities, or places where the function is not continuous, or possibly we have the third type. Maybe there is an asymptote at c. A vertical asymptote at c. So in these three cases, holes, jumps, and asymptotes, plan A doesn't work. We can't directly substitute c in. So now let's dive into some problems. And in this first set of problems, and this should all, you don't have, so let me go back to this. You don't have to know what the graph of the function looks like. I'm just using this as a way to sort of visually explain when direct substitution does work and when it does not work. Okay, so in these three cases, or these four cases here, and in any limit problem, your first attempt should be, can I do this? Can I plug in the limit value for each value of x? And in this case, yes. So this should be equal to the square root of 3. So let me color code this a little bit. 3 plus 6 divided by 3 plus 2. So we're basically plugging in 3 for x, and we don't run into any problems by doing this. On top, we get the square root of 9. On the bottom, we get 3 plus 2 is 5. So our answer is 3 over 5. In this second case, over here on the right, the limit as x approaches 0 of 3x minus 2 to the fourth. Yeah, we don't run into any problems plugging in 0 for x. So we'll put a 0 in for the x. 3 times 0 is 0. So it looks like we have negative 2 to the power of 4, which is positive 16. Okay, same thing down here on the bottom left. The limit as x approaches 1 of cosine of pi x over 3. Well, direct substitution. That looks like the cosine of pi times 1 over 3, or just the cosine of pi over 3, and the cosine of pi over 3 is 1/2. Okay, simple as that. When you can plug in the limit value, or when you can apply direct substitution, these problems are not too bad. Okay, last one. The limit as x approaches 7 of the secant of pi x over 6. Okay, so that's looking like the secant of pi times 7 over 6. Okay, so we have the secant of 7 pi over 6. And if you want to convert to cosine, this is the reciprocal of the cosine. This is 1 over the cosine of 7 pi over 6. And the cosine of 7 pi over 6. So 7 pi over 6 is down in quadrant 3. So the cosine of 7 pi over 6 would be negative root 3 over 2, or negative 2 over root 3. Okay, and we probably want to rationalize that denominator. So let's say negative 2 root 3 divided by 3. Okay, so plan A, this should be the first thing you attempt in evaluating a limit. Can I directly substitute the limit value? Now let's look at some examples where that does not work. Okay, so in this first one on the left, if we were to plug in negative 2 for x, so let's try that, equals 3 times negative 2 squared plus 5, I'll skip the negative 2, minus 2. Okay, so we're plugging in negative 2 anywhere you see an x. Well, immediately on the bottom you see you get a 0, and in a fraction you cannot divide by 0. So this is a situation where direct substitution fails. Same thing with this problem on the right. If we plug in 4, so let's do it like this so it's a little quicker. We plug in a 4 everywhere there is an x. So 4 minus 4 over 4 squared minus 16. In this case, we get again a 0 on the bottom. It doesn't matter if you get a 0 on the top. 0 over 0 is still undefined. So in both cases, direct substitution does not work. Okay. This one gave us 0 over 0. And this one on top, let's see, 2 squared is 4. That's 12. Minus 10 minus 2. Again, 0 over 0. Even if you got 5 over 0 or negative 3 over 0, as long as there's a 0 on the bottom, it's undefined. So let's do something else. Manipulate the expression to eliminate the issue. And the issue in both of these cases is here. The issue is here. In the denominator, plugging in the limit value gives you a 0 in the denominator. So let's try to deal with that. one common approach is to factor. So let's come down here. So this is the limit. Now we haven't applied the limit yet. The limit as x approaches -2 of, well, we could factor the top. So that's a 3x and an x. We need a 2 and a 1. That needs to be positive. That needs to be negative. And we have still an x plus 2 on the bottom. Okay. So it looks like the x plus 2's cancel. So now we have the limit as x approaches, not 0, as x approaches -2. And all we have left is the 3x minus 1. And now we can directly substitute. So basically, you want to directly substitute in the limit value as soon as you can. If you could do it in step 1, do it in step 1. If you have to do a little bit of algebra first, do some algebra, and then substitute in the limit value. So we'll plug in a -2 for x. So now we'll actually apply the limit. So we'll x equals -2. 3 times -2 is -6. Minus 1 is a -7. Okay, same thing on the right. Same approach. Looks like we could factor. So let's come down here. So this is equal to the limit as x approaches 4 of x minus 4 on top. And on the bottom we have a difference of squares. So that will factor to x plus 4 times x minus 4. Okay, the x minus 4's cancel. So we're left with the limit as x approaches 4. We have a 1 on top, and x plus 4 on the bottom. And now, as soon as we get to a point where we can plug in this limit value, we plug it in. Okay, so this is, now we evaluate the limit. So that's 1 over 4 plus 4. So we have 1 over 8. Okay, so this is one. So this plan B, manipulate the expression first. It's not always going to be done by factoring. Factoring is one approach you may want to try. So let's look at another problem. Doesn't look like we could factor here, and it looks like we definitely can't plug in 3 for x, because that will give us 3 minus 3 on the bottom, and that'll give us 0 on the bottom. So immediately we could tell we cannot directly substitute. So another common approach, when you have a binomial, especially a binomial with a radical, you could try multiplying by the conjugate. And it's not always the numerator, we can multiply by the conjugate of the expression that contains the radical. So let's multiply by the conjugate of the numerator here, square root of x plus 1 plus 2 over square root of x plus 1 plus 2. Okay, so we'll multiply across the top, we'll multiply across the bottom. So we have the limit as x approaches 3. So on top, first times first gives us an x plus a 1. And the whole reason behind using the conjugate is because the two cross terms, or the two middle terms, cancel out. We have a, let's do that. We have a positive 2 times the square root of x plus 1, and we have a negative 2 times the square root of x plus 1. So they cancel each other out. And then we have last times last, negative 2 times positive 2 is a minus 4. Okay, so let's FOIL out the bottom. First times first is an x times square root of x plus 1. Outer times outer should be a plus 2x. Inner times inner, we have a minus 3 times the square root of x plus 1. And last times last, we have minus 6. Okay, so on top, let's simplify that. We have the limit as x approaches 3 of x minus 3. Now, I'm gonna reorder these terms, which is fine as long as you keep the right sign with the right term. Let's put the x plus the terms with the square root of x plus 1 first. Then there's a positive 2x and there's a minus 6. Okay, so let's we obviously can't factor the entire denominator, but we could factor these two terms and we could factor these two terms. They each share common factors, so we could factor by grouping. Okay, so we have the limit as x approaches 3. So on top we've got the x minus 3. On the bottom, if we factor out the square root of x plus 1, we're left with an x minus 3. Okay, this is starting to look like we may be able to do some canceling, but we still have the rest of the denominator. And here, if we factor out a 2, we're left with, again, an x minus 3. Okay, so now we have two terms on the bottom. They share a common factor of x minus 3. So now we have the limit as x approaches 3 of x minus 3 on top. Let's factor out the x minus 3 on the bottom. And we're left with, looks like the square root of x plus 1 and a plus 2. Now we're looking good. X minus 3 on top, x minus 3 on bottom. They cancel. So now we have the limit as x approaches 3 of 1 over the square root of x plus 1 plus 2. Now, notice we have not done any calculus yet. This is all algebra. The calculus the calculus happens here when you evaluate the limit, when you plug in the limit value. And now at this step, this is the first point where we can plug in 3 for x without giving us a 0 on the bottom of a fraction. So this is the first time we could plug in 3 for x without breaking a rule. So we could plug in 3. So that should be 1 over the square root of 3 plus 1, which is 4. So it looks like, let's go back to blue, we have 1 over 4. So down here, this is the step where we used calculus. The rest of this was algebra that was necessary to apply the calculus. Okay, so we've talked about applying some algebra to evaluate a limit. Maybe it's factoring and canceling. Maybe it's using the conjugate and canceling. So here's another problem. So let me rewrite this so it's a little more. Limit x approaches 0. So this here is a fraction. So we have 1 over 2 plus x minus 1 over 2 all over x. Actually, let me put this limit out front a little bit more. We have the limit as x approaches 0. Okay, so again, we can't obviously plug in 0 for x because there's a x on the bottom. That would give us 0 on the bottom. Okay, so we immediately rule out direct substitution. So what can we do here? Well, we have two fractions on top. Maybe we could sort of try to simplify this expression by putting those two fractions together. And let's get a common denominator. Okay, so we'll multiply the first fraction by 2 over 2, the second fraction by 2 plus x over 2 plus x. Okay, so we have the limit as x approaches 0. We have an x on the bottom. We got a common denominator on top of 2 times 2 plus x. And let's see, on this first fraction we have 1 times 2, so that's a 2. Second fraction, so we're subtracting a 2 plus x. So it looks like here we could do a little bit of simplifying. Okay, so we have the limit as x approaches 0. On top we have 2 times 2 plus x. And so we have 2 minus 2, the 2's cancel, and then we have a minus x, so there's a negative x there. Oh, so it looks like this x and this x cancel. So we're down to the limit as x approaches 0, negative 1 over 2 times 2 plus x. So remember, you want to directly substitute in a limit value as soon as you can. And at this point, now there's no issue with plugging in a 0 for x. If x is equal to 0 at this step, we have negative 1 on top. 2 times 2 plus 0, 2 times 2 is 4. So, negative 1/4. So you've already seen a variety of different approaches to evaluating limits. So it's not the most straightforward process, and there's definitely not a sort of how to solve limits that works 100% of the time. Sometimes you just have to try different things. And now finally, we may be able to apply one of the two special limit formulas, for one for the sine and one for the cosine function that we've discussed. So we have the limit as x approaches 0 of sine x over x is equal to 1, and we have the limit as x approaches 0 of 1 minus the cosine of x over x is equal to 0. So these are our two special formulas. The first one we proved using the squeeze theorem, and the second one we proved using conjugates. Okay, so this first problem almost looks like this first formula up here, except we have our angle is 3t and our denominator is not 3t, it's 2t. So those two have to be the same. To apply this formula, you have to have the same angle as you have denominator. Those have to be the same. Okay. So we'll just apply a slight manipulation here. So the limit, as in this case it's t goes to 0. Well, let's bring that 2 out front. Let's get rid of the 2. So we have sine of 3t over t. Okay, so now what we could do is we can multiply a 3 on the top and a 3 on the bottom. So the 3 times 1/2, okay, so now we have the limit as t approaches 0 of 3 over 2 times the sine of 3t over 3t. And the 3 over 2, that's a constant. That has nothing to do with the t. So the limit is not affecting this 3 over 2. So we could bring the 3 over 2 out front. And so we have times the limit as t goes to 0 of the sine of 3t over 3t. And so this, according to our formula, this is equal to 1. Okay, so when we evaluate this limit, according to this previously established formula, we have 3 over 2 times 1, or just 3 over 2. Okay, so if the expression in your limit in some way resembles one of or both of these two formulas up here in the top right, you may want to see if there's a way to sort of manipulate things to make it look not resembling one of them, but in exactly the same form. So if we look at this second problem down here, well, same thing. It looks like we've got a sine x and an x. We've got a 1 minus cosine x and an x. So we have two x's on the bottom, x times x. So this is like the limit as x approaches 0. Well, we've got sine x. Let me switch to blue here. 1 minus cosine x. And instead of x squared, let's say x times x. So we could take one of these x's, put it with the sine function, and one of these x's and put it with the 1 minus cosine. Okay, so we have the limit as x approaches 0. Now we have sine x over x, and we have a 1 minus cosine x over x. And we can split this up into two limits. The limit of a product is equal to the product of the limits. So that's the limit as x goes to 0 of sine x over x times the limit as x goes to 0 of 1 minus cosine x over x. And we have a formula for each of these. So we're again applying, well, in this case, we're going to apply both of them. So this should be equal to 1 times 0, or 0. Okay, so we've done a lot in this video, and we have not covered every single type of limit that you might see out there, but these are some common situations, applying some special trig formulas, maybe simplifying. So, anytime you see fractions inside of fractions, that's an indication that it's not guaranteed to work, but it's very commonly going to work if you simplify and get rid of the compound fraction. We talked about using the conjugate. Again, this was a pretty good bit of algebra involved in this problem. We talked about factoring, canceling, simplifying, but in all of these cases, you have to do something and then directly substitute. So plan A, if you can, directly plug in the limit value for x. If you can't, that's when we have to do something else to get to a point where we can plug in the limit value. Okay, so that does it for this problem. In the next video, we will talk about infinite limits. So in this case, each of these limits, or as x is approaching a specific value, well, what happens if x is approaching infinity? Okay, that does it for this one.